this video, we are going to try solve this problem. Okay, so this is 2.2. Okay, from Mechanics of Materials by Andrew Peitel and John Q. Salaas, second edition. Okay, so the problem states, okay, the following data were obtained during a tension test of an aluminum alloy. The initial diameter of the test was 0.505 inch and the gauge length was 2 inch. Okay, so these are the following given data. So load, we have load, elongation. Okay, so this is just a continuation of the load and elongation. Okay, so it starts from 0. Okay, it gradually increases its load until it comes to fracture. Okay, so where it fails. So it says plot the stress strain diagram and determine the mechanical properties such as the proportional limit, modulus of elasticity, yield stress at 0.2% offset, ultimate stress, and nominal rupture stress. Okay, so this is the entire problem. Okay, so let's go to the solution. So this will be our solution. Okay, so what we okay, so let's zoom it. Okay, so this is how we do things. Okay, so first we define what is stress. Okay, so if we go back to the problem, okay, so it says we plot the stress strain diagram. Okay, so in order to that we can plot the stress strain diagram, we need to define what is the general formula for the stress. So we know that the stress is equivalent to the applied force. So in this type, we have load and then over the area. Okay, so here the diameter of the test specimen, I mean the initial diameter, is 0.505 inch, which means that the formula for the load, okay, for each of these will be equivalent to this. Stress is equivalent to load over area. So it will become load over the area of the cross-sectional area, which is pi over 4 times the diameter. The diameter is 0.505. So therefore, pi over 4 t squared, since it has a cross-section area of circle. And then the strain is equivalent, as always, equivalent to the elongation, or let us say the deformation. Okay, so the other term for elongation is deformation. Okay, so we can say it's deformation over the length. And the length of the specimen from the question is obviously the gauge length is 2 inch. So therefore, it is equivalent to the given elongation or deformation over the length. So here, this is the load. So we just copy everything from here. So this and this, and then the equivalent elongation. And from that, we computed the strain. The strain is equivalent to elongation over the length. So it's just here. Okay, so this column over 2 inch, so that we can find the value of strain. And then the stress is equivalent to the load divided by the cross-sectional area. And the cross-sectional area is pi over 4 times 0.505 squared. Okay, so to make the long story short, so we get all of this. Okay, so how do we, okay, so the question is, how do we identify what is the proportional limit? Okay, so here, what's the proportional limit? Okay, so one thing is we need to see also, okay, there is also a portion for stress strain diagram here. Okay, so as you can see, we can, okay, so from here, okay, so from the strain and the stress, okay, So the x-axis here is the strain, and then the y-axis is the stress. So it's easier for me to plot using the Microsoft Excel. Okay. So from the formula, okay. So from load and elongation, we got the strain and the stress. Okay. So here, obviously, we can look upon the values of strain. So as you can see, the strain is constantly increasing at a rate of 0.011. Okay? 0.011, 22, 33, 44, 55. And then again, after that, it jumps into 0.075. So therefore, the proportional limit is here because it is the end value or the final value in which the strain is increasing at an approximately steady rate. So this will be our proportional limit. And here, the proportional limit is the equivalent to the stress of 57,914.24 psi. So if you convert it into KSI, you just divide it by 1,000. So it's approximately 58 KSI. Okay? And then the next question is, okay, so it's just easy for proportional limit. So how about the modulus of elasticity? Okay, so the modulus of elasticity is equivalent, okay, to any value of stress, okay, divide strain. So elongation is the ratio between the stress and the strain within the proportional limit. So here we go. Okay, so we know the proportional limit is here. It has a stress of 57,914.24 psi, and what you need to do is you just divide the stress and the strain at that portion, and approximately we can compute the strain. Okay, so the E is the stress over the strain on the proportion along the proportional limit. So here's the value of stress and strain. You just divide it. You get 10,529,861.58. Okay, so this is its value is in actually its value is in PSI here. So it's in PSI. Okay, so you can convert it into a form of scientific notation. Okay, so in scientific notation, you can name this as 10.53 times 10 to the 6th PSI. So this will be your E. Okay, so just remember, you can compute the value of E by dividing the value of stress over the value of strain at the proportional limit. Okay, at the proportion, use to divide the stress by the strain at the proportional limit. And next, what is asked here is the yield stress at 0.2% offset. Okay, so when computing the yield stress, okay, so we need to look upon the diagram. Okay, so just a warning, okay, so just a reminder that in finding the yield stress in the along the stress strain diagram is just approximation. Okay, so here we need to draw a tangent line in which is tangent to the curve back of the stress strain diagram. Okay, so in this diagram, this is the back of your crooked back of your stress strain diagram. You draw a tangent line along that, and approximately this is 69 KSI. Okay, so this is approximately around 68 or 69 KSI. So that is your yield stress. But here, okay, by just looking upon the diagram, it is the nearest value is here. Okay, so that's why our answer for the yield stress is approximately 69,896.49 KSI. Okay, so but somehow this is just an approximation. Okay, this is approximately the location of this tangent line, the value of tangent line. So this is just, so if your answer is 69,000 psi or 69 KSI, it could be also be considered as correct. So since this is just a, what we call here, an approximation. Okay, so this is the approximate location for your yield stress. What about the ultimate stress? Okay, here, ultimate stress and nominal rupture stress. Okay, the ultimate stress is just simply the highest stress in the stress strain diagram. So here we could see along this graph, okay, the highest is this 73,890.58 psi, or we can convert it as approximately 74 KSI or 73.89 KSI. So this is your ultimate strength. The highest abscissa or the highest value here is the stress strain diagram. So if you're looking upon the stress strain diagram in which you are not using Excel to solve this problem, you can estimate it as 73 KSI or 74 KSI. So this is the nominal strength. What about the nominal rupture stress? Okay, so how do we compute the nominal rupture stress? Okay, so if you can see upon the figure here, okay, so there is no value actually for elongation at this portion in which it fractures. Okay, so but by looking upon the diagram, we can actually extend the value. Okay, so as you can see, at near the end of the stress strain diagram here, this is strain, this is stress, so it gradually increases 0.01. So we just continue it to increase up to 0.01 at the strain. Okay, so we just drag it down. The same formula, the stress is equal to the load divided by the cross-sectional area, which is pi over 4 times 0.505 squared. So we get 67,899.45. Okay, so the nominal rupture stress is the value of the stress at the point of fracture. Okay, so nominal rupture stress is the value of stress at the point of fracture. So here, it is usually smaller than the ultimate strength. It is actually smaller than ultimate strength or ultimate. Okay, so we get 67,899.45 psi, or you can round it to 67.9 KSI. So that is how you compute, okay, the proportional limit, the modulus of elasticity, yield stress, ultimate strength, and nominal rupture stress, okay, of this problem. Okay, so I hope you understand something. Okay.